So we looked at this example of there being a motor that was connected up. Let's say we've got a bearing here, maybe like 2 bearings, hopefully. And then some internal bearings. We'll say all of the bearing damping is B. Let's connect it up to a spool. Remember this winch problem? Connect it up to a spool that has cable wrapped around it. And has some sort of load, sort of mass hanging from it. Wow. Okay. And we want to model this dynamic system. Let's actually model it all the way back to the electronic system, which say is being driven by some voltage source. And some motor. It's turning this spool, and so this is pretty much your standard winch. In a lot of cases, you're going to have a gearbox on this motor so that you can change the torque speed characteristics, run it more efficiently, that type of thing, or get more torque out of it. But we'll ignore that for now. Maybe later we'll do one where we also have a gearbox in there. Gearboxes are something we can handle now because we have transducers, but in this one problem I thought maybe it would be good to just do this. This is the one we looked at before, but remember we modeled the motor as a torque source, and then we had this weird like torque source relationship here on the motor. Oh, I realize you guys can't see my face on the screen. I know that would make you sad. I know you guys would be sad if you didn't have that. Oh, that's me. Thank you. Extra points. Okay, so let's do a model. We're just starting to get used to modeling with motors, but let's do a motor model. Let's do a model of this spool, okay? And actually, you guys have already seen some discussion of the motor model, so we'll focus on the spool at first. We'll do a little dynamic model of the spool. So the spool is going to, if we looked at it end on, the spool looks like this. We've got some radius of the spool, and it's also got some angle of rotation, theta. And we also have the distance that the mass moves. And we'll call that x. So we want to relate the variables here that describe the motion of the spool to the motion of the mass, and they're related by the arc length of this spool's rotation, right? So when you move through an arc length of r times theta, this thing moves r times theta in x, right? So when you move through theta, this thing moves r times theta, the circumference of that arc length. Or that arc length, I should say. So the relationship is r theta equals x. And since we like to work in angular velocity and translational velocity, we take the time derivative of this. We have r omega equals v, where v is the velocity of the mass. We're assuming here that there's no stretch in the cable. We're going to assume that throughout this problem. It's a little bit more complicated if you don't make that assumption. Cables actually have, so if it's like a steel cables do have some stretch to them. And if you want to take that into account, that's totally fine. It does create a nonlinear problem, though, because the spring constant associated with that cable depends on the length of the cable. So how much you've got in your spool, or how much is spooled out at that time, changes that spring constant. So you end up with a nonlinear model. It's okay to have a nonlinear model, but we're not going to consider that now. It's more complicated. Hopefully I'll have a time to talk about those a little bit, though, in the future. So here we go. We've got this relationship here, and the transformer ratio. Remember, transformer ratios are defined as being the across variable of side 1 divided by the across variable side 2. Since our power flow in this problem is primarily going to be, driven by this source, right? Through the motor, through here. We're going to call this side, so we'll call this the rotational side, side 1, and the translational side, side 2. So the across variable ratio is equal to the transformer ratio. So we have two transformers in this problem. I'll call this TF12. And this is a relationship that we've just discovered here between omega, which is our across variable on side 1, and v, our across variable on side 2. So it's omega over v. Which is equal to 1 over r in this case. Okay? So that's the relationship there. We found a transformer ratio, and therefore we know we can also relate the torque to the force through this transformer ratio as well. Once you find the transformer ratio, though, right, from either side, so if you find it through the through variable or if you find it through the cross variable, you're done. It's a transformer because the across variable is directly related. If it was a gyrator, the cross variable and the through variable would be related directly. And you'll see that the classic one is a piston cylinder arrangement, where a pressure, which is an across variable, gets turned into a force, which is a through variable. But more frequently, we have transformers. Okay, so we've got that transformer. Let's do a linear graph model. And we have an electronic side, we have a rotational mechanical side, and then we have a translational mechanical side. So they're each going to have their own ground. Let's go ahead and put those grounds in first, maybe. So we have the electronic system, the voltage equals 0. We have the rotational system where the angular velocity equals 0. And then we're going to have the ground for the translational mechanical system where we can say the velocity equals 0. Okay. For a motor model, what we'll often do is we'll say, okay, we have a voltage source. Since I didn't talk about like what is the plus and minus terminal of the motor and all that stuff, I'm just going to assume that our positive connection here is positive to the motor. It would be weird if we chose it differently. And what we'll do is we'll use the internal resistance and inductance of the motor we'll include in the circuit. So we'll have a resistor R, And then we'll have an inductor, L. And then we'll have, you could switch those too, L and R. They're both part of the armature windings, so we could swap them. You know, they could be one, L could be first, then R. It's sort of arbitrary. Then we have this interaction that happens between the armature and the rotor, right? So we have the rotor that's going to be spinning, and for this DC motor, we'll have this interaction here. We'll say that this side, we'll call this side, since we're going to call this transformer 1, 2, we'll call this one 3, 4, kind of annoyingly, but it's kind of what we're stuck with here. It's going to interact with the rotational side through the rotor. That was kind of a weird wiggle. So this is 4, and we know it's a DC motor, so it's got a nice transformer relationship, and we'll call that TF3, 4. And this rotational side here has got a few things going on. It's got that interaction with the through the motor. Its shaft, though, has some bearing damping on it, right? We've got the external bearing, which is on the same shaft. We'll assume this shaft is relatively short and stout, so it doesn't have a lot of twist in it. So we'll ignore any twist. And the bearing damping and the moment of inertia of the rotor, all that stuff, we can model them as all having that same angular velocity. So we'll put them here. So we'll say this is J, and the bearing damping B. And then we also have that same angular velocity through the spool interact with this translational system, right? So we have another transducer. Yeah?
So the bearing is just one, because velocity is like 2 damper.
Yeah, you're probably going to have 2 bearings out here at least, and then you're going to have some bearings in the motor. Let's say they all combine to have 1 bearing damping B. We could draw multiple and combine them, but let's say we've done that previously and we've got it down to 1 damping coefficient. That's also very practical because oftentimes we find this through measurement. So you take into account all the bearing damping in one parameter because often you have to measure it anyways. Okay, so we've got B. And then we have this interaction through the spool. So the spool, so this was the motor interaction. This one's going to be the spool interaction. And that one we have side, we called this side 1 before. And we have it interacting with side 2. And on this translational side, we have a mass. And we also have gravity, right? So gravity is going to be pulling down. And we can model gravity as being a constant force source, okay? So if we look at this and we say, we've already said that x is going up, right? So that's our coordinate arrow direction. The force of gravity is opposite of that, right? So this is going to be F sub g. So we're going to be going away from the node of application with Fg, which is just equal to the mass times g, right? It's just a constant. Yes?
Why are some of the lines dashed?
The lines that are dashed are for A-type energy storage elements of inertial elements. So if we've got A-types that are rotational mechanical elements or A-types that are translational mechanical elements, they are governed by Newton's second law, right? Newton's second law requires that we have an inertial reference frame for that F equals ma equation. And that's what gives us this connection to the inertial reference frame, the ground. But it's a sort of virtual connection, right? Because the mass isn't actually connected in a direct way to ground. It's just we're referencing its velocity to ground, which is why we do that dashed line. We treat it just like any other element. If you forget to dash the line, it's not a big deal. But we dash it just to remind ourselves that it's a sort of virtual connection. Mm-hmm.
So the ground is pretty much like just the inertial reference frame?
Yes. So the ground is also the connection that B has. So for instance, like this is to some chassis, some fixed point. So it's at 0 angular velocity. So yeah, so it has to be inertial. Oftentimes we take it to be 0. Because that's convenient for most of our velocities. Yeah. Okay, so I think that's a pretty good model.
There's no connection between the 1 and 2?
Oh yeah, so these two elements are interacting. They're also a transformer because they have the relationship directly between the cross variables, and then therefore between the through variables as well. So we'll call this TF12. We already derived what TF12 is now. And TF34, the motor one, we derived in a previous example. Okay, so this is our linear graph model. And we can then do our state space model. So 1A is our normal tree. And let's go ahead and select the elements for that. So as always, all of our nodes are in it. So I'm not going to select them explicitly, but we know they're all in it. Cross-variable sources are first. Remember, with transducer elements, this gets a little bit weird, right? Because we have that extra step in there, and that extra step actually has some caveats to it. So we're going to see one of those caveats in this problem, actually. So we've got the VS here. No other cross-variable sources. FG is force source, which is through variable, so through variable source. So we don't include it. Then we go to A-type energy storage elements. Now we have an interesting thing happen. Remember, we have, instead of just 2 rules, so we used to have the rule that wouldn't allow us to select an element that would create a loop, right? But if we select J, an A-type, and M, an A-type, we don't create a loop yet. But then when we go to do the next one, the transformer rule, which says we have to select one or the other, at least one, oh, actually not at least one, exactly one, precisely one of the branches from the transformer, so 1 or 2 in this case. We can't select either without creating a loop, right? Which implies that one of those A-types shouldn't have been in it. So it also implies that one of those A-types is not independent of the other. So the M and the J are not independent. That's because their velocities are directly coupled, right? The angular velocity of the J element is directly coupled to the translational velocity of the mass. They're directly coupled through the spool, and so we don't have 2 independent A-types here. We have just one independent and the other one is dependent. It's arbitrary which one we choose to be independent or dependent. I want to take the mass to be our independent energy storage element because I'm interested to have the velocity of the mass be a state variable, because the velocity of the mass is one of the things we're going to be interested to look at as an output. Making the velocity of the mass, making that output easy to write, right? If it's a state variable, it's easy to get. So that's just a matter of choice, though. It is really just arbitrary J or M. So if we had chosen J and we hadn't seen that, we would have realized that we made a mistake when we got to the next step and we had to select 1 or 2. And then the correct thing to do is to go back and deselect one of the A types. Okay? So if we had selected J and M in the next step, we would realize that we had made a mistake. So sometimes these rules need to be followed. Even if in that first step it looks like it's fine, it may later show itself not to be fine. I actually added a little footnote to the rules. I mean, this is implied in the rules as they're written in the notes. I added a footnote this morning just to mention this part as being possible. Okay. Then we have the transducer rule. So now we have to select one or the other of each of these transformers. Now, we can't select 2, or we create a loop here. So we have to select 1. And remember, we can't select 4 because it would create a loop, so we have to select 3. Now, if we had the option to select 4 or 3 here, we still would have wanted to select 3, and that's because L here won't be required now to get to this node because we used this element here to get to that node. Otherwise, we would have had to use L, and if L is in the normal tree, it's a dependent energy storage element. So, and one of our rules is that we want to minimize the number of the number of T types in the normal tree. So this is in keeping with that as well. So then we have D types, we have the R. We can't select any of these, so J or B, because they would create a loop. So we're done. We can't select any more elements without creating a loop, so we are done. Okay, so now we have our normal tree. Okay. Primary variables. We have, I'm just going to go along this thing in order just because this has got a lot of variables. So the primary variables are VS, VR, IL, V3. The through variable for this is T, torque 4, TJ, TB. Cross variable is omega 1. Through variable is F2. A cross variable is VM. And then the across variable is V, I'll call it V sub G. Secondary. We have IS, IR, VL, I3, omega 4, omega J, omega B, T1, V2, FM, and FG. Oh, sorry. Yeah, that's these two are switched, right? It's through variables on branches or on links, so that are primary. So good catch. FG is the primary. Okay, 1C are vectors. Oh wait, no, state variables, right? State variables are, we gotta look for A-type branches. I see one A-type branch, it's M, so it's a cross variable is a state variable, VM. I see one T-type link, it's L, and its through variable, IL, is a state variable. Now we're to the vectors. Oh, what order is the system? Yeah. Very good. For vectors, I have my state vector, which is VM IL. Input, which I've got two of them. I've got my voltage source, and then I've got my gravitational force. And I have my output, which we haven't specified, but I think we want to look at the velocity of the mass. And let's also find out how much torque the motor is supplying, which is torque 4, right? Yes?
You always have to choose, like in this case, those are all 1 by 2. You always have to choose.
That's just an accident. So the state vector is whatever, n, the order of the system, an n vector. U is the number of inputs. We happen to have 2 in this case. And then y is the number of, the dimension of y is the number of outputs. So we chose 2 arbitrarily. I'm just interested in 2 variables. So, okay, elemental equations.
If we were like masochists, we could just put like every variable that
Yes,
we want to start.
absolutely. Yeah. So let's list our elements here. So I'll just do them in order here. R, L, 3, 4. Then it was J, B. And then it was 1, 2. And then it was M. No, that's a source. So these are all of our passive elements here.
What was the y vector again?
VM and T4. Okay, so the elemental equation for the resistor is just good old Ohm's law. VR equals IR times R. For the inductor, DIL dt equals 1 over L VL. Okay, 3 and 4 are related to the motor, right? It's a transformer, so it always has the relationship that, so it's omega 4 equals the 1 over TF 3/4, the transformer ratio of the motor, times the cross variable associated with 3, so that's V3, the voltage across 3. And the torque 4 is equal to negative TF 3/4 times the through variable I3. Okay, So these equations, it's not like this is the 3 equation, this is the 4 equation. They both have 3 and 4 in them. I just write 3 and 4 so I remember to write both equations down. And then J, we have d omega j dt equals 1 over j tj. TB equals b omega b. And 1 and 2 are related through the spool in the same way. So we have our cross variable output here, which is v 2 equals 1 over tf 1 2 to the cross variable on the one side, omega 1. And we have f2 equals negative tf 1 2 times the torque on the one side. Finally, we have our velocity of the mass differentiated in time equaling 1 over m fm. Okay, now what I want to do is I want to finish this up and do the continuity and compatibility equations. I know if you guys can't stick around, it's okay, but it'll take us about 5 minutes to finish this up. So the elemental, now we're ready for the continuity. Equations. The continuity equations, we need one for each passive branch, right? So we'll just go down the line here. This one can use this contour. It just says that IR equals IL. So the R has IR equals IL. For 3, I will ask you to not have conversations in the classroom as you leave. So 3 here is the next one, and it tells us that I3 equals IL. So I3 equals IL. And here we've got the torque 1 leaving the contour, so that's to equal everything going into the contour, which actually everything's actually going out of the contour, so they're all negative on the other side of the equation. So we have T1 equals T4, or negative T4 minus TJ minus TB. So this is for, this is actually for 1 here. So we have T1 equals negative T4 minus TJ minus TB. And we've got this guy here, which tells us that FM equals everything going in, which is nothing, so everything is going out, negative F2 minus FG. So I have FM equals negative F2 minus FG. Okay, great. Now we have our compatibility equations. Compatibility equations correspond to each link. So if we put the link for the inductor L in, we would create this loop. So we have VL equals negative VR plus VS minus V3. So we have VL equals negative VR plus VS minus V3. And the 4 element here is also a link. If we put it in, it has this loop here with 1. It's actually the same as J and B, right? Omega 4 equals omega 1, omega j equals omega 1, omega b equals omega 1. So we can do all of those, 4J and B. So 4 has omega 4 equals omega 1. Omega J equals omega 1. And omega B equals omega 1. And finally, the last one we've got is the 2 link, which just says that V2 equals Vm. So we've got V2 equals Vm. Okay. So at this point, you know, our 2A would be to do these substitutions directly across, right? These ones actually you have to go down here, and then like that, and then straight across. This one. This one's also straight across. This one also crisscrosses. It's just sort of an accident that it crisscrosses, because we didn't really have an idea which one was going to go where. And then this. So you could do all those substitutions, and then you could hopefully eliminate it down to 2 variables. Now, the algebra can get a little bit messy for something with a lot of transducers in it. I would recommend using the statement software, either the web app or the Python module, Python package, to do this part. But yeah, or the Mathematica version too. So that's pretty much this problem. Second order system. We did it right this time. This is a dynamic model. So, all right.